The central nervous system has in principle two parts, one which is the brain and the other which is the spinal cord. And we are working on both these aspects. For the brain, there's good news and bad news in terms of its architecture. The brain is isolated from its surrounding by a structure which is called the blood-brain barrier, which separates the brain from the circulating blood. As the name implies, the blood-brain barrier poses a barrier which, when it is intact, is good news, namely it prevents all the materials in the blood, or most of the materials in the blood, from entering the brain proper. That's important and that's good news because you have to confine the brain within its own environment. The bad news is that this blood-brain barrier is not selective just in preventing blood-borne materials, everyday blood-borne materials, from entering the brain, but it also prevents valuable and important drugs and treatments from reaching the brain. So the problem of treating life-threatening solutions that impair the daily life, solutions that are related to psychiatric diseases, for example, or other diseases such as brain tumors, is that in most cases the highly efficient treatment modalities such as drugs, chemicals and other compounds will not be able to reach the brain because they cannot cross the blood-brain barrier. Now, in order to overcome this problem, it is very important to have a structural and functional understanding of the blood-brain barrier. An impediment to this understanding have been the current models of the blood-brain barrier, which do not take into account that, as everything else in the body, also the blood-brain barrier is a three-dimensional structure, and moreover, the blood-brain barrier has on its blood side blood flow as a major component that regulates the barrier function. In order to study blood-brain barrier and to develop better treatment modalities for brain-related injuries and brain-related diseases, we are working on developing a more reliable, a high-fidelity, three-dimensional model of the blood-brain barrier, which incorporates in a proper geometric arrangement all the cells that are involved in this blood-brain barrier, and moreover, on the side of this, which models the blood flow, indeed provides for the flow of a liquid similar to that of blood. With this model, we hope that we will be able to unravel some of the fundamental mechanisms which provide for this barrier, but which also can be used then to overcome this barrier selectively to allow the passage of drugs from the bloodstream into the brain. The other aspect of the central nervous system is injury to the spinal cord, and I believe spinal cord injury has become very prominent in this country through the ordeal and eventual death of Christopher Reeve, the Superman, who fell off the horse and ever since was injured his spinal cord, and ever since was quadriplegic and eventually succumbed to this terrible disease. One of the main and most interesting traits of this study of our laboratory is to study how we can repair the spinal cord and how we can functionally again connect the two parts that have been severed, and when there's a gap which will, under normal circumstances, never heal. We have developed some smart scaffolds, and we are using innovative approaches to try to bridge the two parts of the severed spinal cord. Particularly, we have come up with a notion that as blood vessels can grow, and as normally during development nerves grow along these growing blood vessels, we are trying now to span the gap between the two severed parts of the spinal cord by inducing blood vessel growth. And through this blood vessel growth, guide the nerves to enter the spinal cord, the severed section, the scaffold that combines the severed sections of the spinal cord, and then get into this scaffold and transverse the scaffold, and then eventually hook up with the nerves downstream from the severed areas.